Let's look at Lenz's law. So remember that Lenz's law says that the current induced will create a magnetic field that opposes the magnetic flux that induced the current. So in practice, this is what happens. Let's say that we have a loop of wire and there is no current going through it or anything like that. It's just a plain old loop of wire. But it is in the vicinity of a current carrying wire. And let's say that there is a current I going up. So by the right-hand rule, the second right-hand rule, if we place our thumb in the direction of the current and then look at the direction of the magnetic field, we'll notice that everywhere on the right side of the current, the magnetic field will be into the page. Everywhere on the left side of the current, the magnetic field will be out of the page. Okay? Now, our area of interest is, of course, the right side of the current, because that's where that loop of wire is. So essentially, the loop of wire is sitting there in the magnetic field of current I. Now, if we, let's say, increase I, so increasing I means that B will increase. Right? Because the magnetic field due to a current carrying wire, a straight current, is mu naught I over 2 pi r. So increasing I will increase the magnetic field. So if originally the magnetic field was into the paper, into the loop, like this, and then we are increasing the current, we are changing the magnetic field by increasing it. So the increase is also in the direction of the original magnetic field. So Lenz's law says that this loop is no longer comfortable sitting in the original magnetic field because now the magnetic field changed. But it can do something about it, and that something is induce its own magnetic field to oppose the change. So that means that the direction of the induced magnetic field and the direction of the change are opposite of one another, and the magnitudes are the same. So B induced is in the opposite direction of the change in the magnetic field, but the induced magnetic field was created by an induced current. And to figure out the direction of that current, we have to place our hand inside the loop with the fingers coming out of the page, which then means that the current, the induced current, will be counterclockwise. Okay? Let's look at another example. Say that we have a magnetic field into the page. And let's say that there is a loop of wire in this magnetic field. And suppose that this loop is conducting, but also elastic. So let's say that we're stretching out this loop. So what that means is that we're increasing the area, which means that there will be more magnetic field lines crossing that area. So the magnetic flux is changing. So if originally the magnetic field was going into the loop, I'm sorry, that's B original, not B induced. So we have the original magnetic field is going into the loop. And then when we're increasing the area, we're picking up more magnetic field lines. That means that the magnetic field, the change in the magnetic field is also going to be into the page. Well, now the loop is able to do something about that. It does not like the change. So it will induce a magnetic field to oppose the change. So these two have to be in opposite directions, and then the magnetic fields, the magnitudes are going to be equal. So the current that induced this magnetic field, we can figure out the direction of it by doing the right-hand rule. So again, our fingers are going to be inside the loop, pointing out. So then the thumb is going to circle around in a counterclockwise direction. So, looks like both examples that I gave you have the same direction for the induced current. So I guess we can look at other examples. So let's say that we have a loop of wire, and I'm gonna place a current I under here, under the wire, under the loop. So the current in the straight wire will produce a magnetic field around it. That means that everywhere above the current, by the right-hand rule, the magnetic field will be out of the page. So place your thumb in the direction of the current, and the bent fingers above the current will come out of the page. Like this. And we really don't care about it, but below the current, the magnetic field will go into the page. So that is the magnetic field due to the current. So now let's say that we are moving the current down, so away from the loop of wire. So now move I down. Since the magnetic field is mu naught I divided by 2 pi r, the further away we are from our area of interest, from our loop, the weaker the magnetic field will become. So while originally the magnetic field through the loop was out of the page, and now the magnetic field is decreasing, the change in the magnetic field will be in the opposite direction. So that's delta B. The loop itself does not like the change, so it will induce a magnetic field that opposes that change in the opposite direction of the change. So coming out of the page. Which means that the induced current will be given by the second right-hand rule. We place our hand inside the loop with our fingers coming out of the page, and our thumb will go, oh no, again, counterclockwise through the loop. Now, in the 3 examples I showed you, the current is going counterclockwise in the loop, and that's just a coincidence. I'm just making these examples up as I go along, so accidentally the induced current is counterclockwise. Let me think of another example where the current will go in the opposite direction. I guess in this same example. So let me redraw this. So here is current I, and here is the loop of wire, and the magnetic field initially above the wire is out of the page, into the page below the wire. Let's say that we are increasing the current through the wire. So we're not moving it, but we're increasing the current. that means that the change in B is also increasing. So while originally the magnetic field through the loop, inside the loop, was coming out of the page and the magnetic field increased, then the change in the magnetic field is also going in the direction that the original magnetic field was going in. So then the induced magnetic field will want to oppose the change by creating a field that is in the opposite direction of the change and the same in magnitude. So now when I place my hand with my fingers into the loop in the direction of the induced magnetic field, then I get a current that is clockwise. So that's the induced current is going to be clockwise through that loop. All right, I hope this helps.